Okay, and good morning to everyone. And that was Jim Morrison, The Doors, and Break On Through to the Other Side, and that's what we're trying to do, break on the other side of the semester. Last week, today, tomorrow, and Thursday, last 3 days of lecture. And we, yesterday, spent our time on graphing, and I'm hearing comments about graphing. And so we got up to what, 20, what was it, Marisol, before we had in trouble? Up to 40. Okay, so up to 40, we're okay. The last 10 or 11, you're indicating we're troubles. So let's take a look at that. This is section 9.3. And let's look at what we have there. Let's look at number, was 40 okay, or did you have questions in 40? We have questions in 40. Okay, this is the problem that we have. It is a two-variable linear system. There's our equation, y equals negative 3/4 x. End of story. Now, let me write that on the board up here. Y equals negative 3/4 x. Okay, the first thing I'd like you to realize is that if x equals 0, y equals 0. So if I try to create some pairs, just looking at pairs of numbers, and this is again what I can do. I can say if x is 0, and I substitute in, y will equal 0. So this happens to go through the origin. Now, doing a two-intercept problem, you can't do. You only get one intercept. So you plug in another x, your choice. So I might just choose to substitute x at 4. If x is 4, y is negative 3. Yeah, if I had up here, so I'm saying if I had y equals negative 3 over 4 times 4, that's really 4 over 1. So the 4's cancel, giving you negative 3. 2 points, that's all I need. Go over 4. So 1, 2, 3, 4. I'm not real pleased with that because with the scale I have, my negative 3 is going to be down here. So let's call this 2, this 4, just so I have the scale so I can use it. This is negative 2, negative 4. So if I think of where 4, negative 3 is, here is the point 4, negative 3, and I have a point right here. 2 points. Well, I know you can get a third to check, but the point is 2 points determine a line. You only get the third point as a checkpoint. So all you need is 2 points, and so I have the graph immediately. So if all I'm asked to do is graph a line, that would do it. Now, if I'd like to get a third point, be with you in a minute. If I'd like to get a third point, it'd be sort of nice to have it in this quadrant so I don't run into some things down here. So maybe let's take x at negative 4. How about x at negative 4? What will that give me? Y equals negative 3 over 4 times negative 4 over 1. Positive 3? Yeah. So that says if I go to the left, negative 4, so here's negative 2, negative 4, then go up the same distance I had here. That's my point up here, which happens to go through. So if I ran this at negative 4, and this is up 3, if I brought this across, so if this is 2, here's my 2, here's my 4, and so I should be about right in here coming across. My scaling is not quite as careful as I'd like. There's my third point. Can I get 4 points? Can I get 5? Yes. 6? Yes. How many points could I get? endless, nicely stated, infinitely many. You only ask 3 so that you make sure that all 3 are on the line. We call it collinear. Robert, you had a question.
Oh, you answered that.
Okay. But does that answer what you have here? Now, just a comment from yesterday. I said that if we had an equation in this form, we called that the slope-intercept form. So the slope is negative 3/4. So m, the slope, is a negative 3/4. So that says if I run 4 units on the x, I'll drop down 3 units on the y. So if I talk about this being a point, if I go 4 more units to the right, that's my run. My rise is negative 3, and there's my other point. Over and up or over and down? Well, the slope is the coefficient of x. If I have y by itself, the coefficient, meaning the negative 3/4, is my slope. Now, this is technically plus 0, correct? So the intercept on the vertical axis was at 0, and sure enough, when you put x at 0, you got y as 0. Okay, well, let's go to another problem, but let's make sure we're okay in 40. So this was number 40. Any further discussion on 40? Okay, then I'm going to move down to 42. Let's go to the document cam. Now, if I look at this problem with the information we just provided, the slope of the line is 4/5, agreed? And it's going to cut the vertical axis where? At negative 1. I'm just going to label these axes. Okay, so I need to go ahead and scale this. So let's go back to the document cam for a moment. Okay, it was 4/5 x minus 1. I need to write that up here. So y equals 4/5 times x minus 1. Now just a comment here. This was set up for you in slope-intercept form. You need to understand that you have an option here. I can take this equation, and I'm going to write it down here for a moment, and I'm going to multiply the left side by 5 and the right side by 5. So that gives me 5y equals 4x minus 5. So far okay? Then I could add 5 to both sides and subtract 5y from both sides and say that 5 is equal to 4x minus 5y. Now, you can just reverse that equality. Remember, if a equals b, b equals a. Now, this particular form of the equation is called standard form, where you have something times x plus something times y equals a constant. The form we're talking about is ax plus by equals c, and we call that a standard form. Same line, it's just a different form. Now up here, this was slope-intercept. This is in the form y equals mx plus b. So this is the slope-intercept form. Now it's interesting that when you have it as a standard form, it makes getting the intercepts, the x and y intercepts, pretty nice. I let x equal 0. So if x is equal to 0, that's out, and I have negative 5y equals 5. So y has to be negative 1. 0, negative 1. If x is 0, y has to be negative 1, and that's exactly what I found. The intercept is at minus 1. Okay? Now, it's not so nice getting the other intercept. What happens if y is 0? Then 4x equals 5, so x has to be 5/4. That's 1 1/4. So if this is 1, and I come over and make that 1 and this 2, where are you going to find 1 1/4? Otherwise, if this is 1, this is 2, and you play a game of halvesies, and then you play halvesies again, and it looks like that intercept is right there. Now, what's wrong with that? Well, essentially, the problem with this is I have 2 points very close together, and I had to estimate where 1 1/4 was. Now, my two ordered pairs, 0, negative 1, that was the y-intercept, and then we had 5/4, comma 0. Again, if y was 0, 4x equals 5, divide both sides by 4, and you get x equals 5/4. Now, that's enough to generate my line. But as I say, the problem is, how accurate am I? And it's a little bit sloppy. Well, what could I do here to get my line? This says if I go over 5, I should go up 4. So the run is 5, the rise is 4. So I start here, and I'm going to go for a run. Sounds like we're jogging. Okay, so we said this was going to be at 1. So there's 1, 2, 3, 4, 5. So there's my run of 5. And then I'm supposed to go up what? 4. Okay, so this was 1, 2, 3, 4. Now, if you'll notice where my line's going, I came pretty darn close to what I should have been. I was lucky in where I tried to locate 1 1/4. Yes? Yes. You can do 2 intercepts. You can do slope intercept. You can just find points that work. So if I make a table, again, thinking of a table of values, now remember this is the third approach, and this is the one that if you're going to get nice numbers is a little bit harder to do. Now 0 minus 1 was nice, but if I want 2 more points so I don't have fractions, that's a little game of mental arithmetic. Now I can do it in either way. I can come up here and set x, or down here. This is a little bit easier to do because if x is, let's say x is 10. If x is 10, what's y? So I'm going to let x be 10.
Why 10?
I chose 10 because 10 is a multiple of 5. 5 will go into 10. It was that simple. Okay, so if I chose 10, and again, Kim's asking, well, why 10? Well, I wanted something I can divide by 5, so I could use a 15, a 5, a negative 5. Okay, so this goes into here too. Gives me an 8 minus 1, so y is 7. So I have to go what? 5 more from here, and up 4 more, and I'll eventually get to 7 and have another point in the line. Yeah, to find points that you can just plug in and have them work nicely. You have to do some mental gymnastics. Yeah, if you're thinking of you have y by itself, then find multiples of that denominator so you have no fractions. Well, x is always, I start x at 0 and ask what's y. And as long as I have a nice integer here, that gives me an intercept that's easy to graph. 0, negative 1 was really nice to graph. Well, as long as I get an integer. Now, if I run 5/4 to get the 0, that's the other intercept, then I've got to estimate 1 1/2, then half of a half to get 1 1/4, and that is a little bit dicey, unless you have some really good graph paper. And I'm asking you not to do it with graph paper because I'm wanting you to draw these coordinate systems. And they should be drawn large. on the paper, like Kim was saying she did in not postage stamp size. So if you're in a blue book, use half of a page to draw your graph in the blue book when you're doing a graph for me. 2 problems per page, yes. Okay, let's keep going. Is there another one of these you wanted to look at? This is from 40 to 50, which is where we seem to have our grief.
What about 45?
Okay, let me come back center. That means turn the page. For 45, I'm hearing 45 and 46. Okay. 45. The problem, these pesky decimals. Pesky decimals. Very seldom, and again, I just want to point out what is ahead of you. In algebra, let me write that down, Ernie. Thank you for leaving up there just a little bit more. Y is equal to 0.4x minus 2.5. Okay, I'm thinking of all the algebra classes I've taught. The number of times I've seen an equation like that, you can put in one hand and not use all 5 fingers. I'd never graph it that way. I would instead say, gee, that's y is equal to 2/5 x minus 5/2. I work it with fractions. I'd never leave it with decimals. Okay? And that creates part of the problem because I want slope. And the slope at 0.4 doesn't tell me anything because how do I go a rise of 0.4 with a run of 1? No. Have a run of 5 and a rise of 2. I want integers when I'm counting off spaces on a graph.
So run at the bottom, the rise at the top.
Yes, rise over run. The sun rises over where you're running. I hope that helps. Okay, let's do 1, 2, 3, 4, 5. Okay, again, make sure that my spacing is correct. 1, 2, 3. Now that's about all I really need in terms of what I'm doing here. I guess I should run the bottom part here. And again, I'm hoping after you've struggled with these, you're going, boy, I wish I knew that yesterday. -2. Now the question. What's my intercept on the vertical axis? 2 ways of getting it. Where is the line going to cut the vertical axis? Called the y-intercept. No. -5/2. Remember, when you have it in this form, now it's the lost part, you're misinterpreting what lost means. You aren't remembering what you have been given as information. If I have this form, what is B? It is where the line cuts the vertical axis. Just a minute. Just remember that. So if I have y by itself, whatever this is called the y-intercept. So this says you're at -2.5. So I'm right there with my point. Again, this form, y by itself, tells you that the part out here is where the intercept is in the vertical axis. The coefficient is the slope. So this says you have a run of 5 and a rise of 2. Here's my run. There was the 5 coming down here. And you're supposed to go up 2. So there's 1, 2. So here's my other point. Have my line. Now, there's a difference between being so lost and just not remembering what you've been given as information. Now, if I have problems with remembering this form, how do I get the y-intercept? It's when x is 0. So put x 0, what do I get? If x is 0, y is negative 5 over 2, which is negative 2.5, which is the point I plotted. Okay, 4/5. 4/10. 4 over 10 coefficient? That's 0.4, correct? 4 over 10 is 2/5, or I said 1/5 is 0.2, 2/5 is 0.4. Back to math 10. Okay? Now, let's say you didn't like that, and you wanted it still in this form. What would you do? You want to pick an x. We're just going to do a table of values. When all else fails, run a t-table. x, y. Okay, I want something times 0.4 that'll give me an integer. What would you like to use for x? I want to get rid of the 0.4. What x would get rid of the point? Okay, it's 0. We've done that one. Give me another one.
Negative.
No.
What do we do with that?
0.4 is a decimal. How would you make it a whole number? Let x be 10. 10 times 0.4 is 4. Right? So if x is 10, then this becomes 4. And what's 4 minus 2.5? 1.5. No, 10 comma 1.5. So you go over 10 and up. So if I'm here, I go over 5 more, and I should be at 1.5. So let's see if it works. This was at 5, we said right here. Okay, so I'm going to make a line right there. Come over another 5. So this means I'm out here at this point, and then I'm supposed to go up what? 1.5, and so this is, I think, what we're doing here. And this was at 1, and so that's at 1.5. Okay, and if I extend my line, pretty darn close. So this was the pair 10 comma 1 1/2 that I had for this point right there. If you didn't like 10, you could let x be what? Minus 10. You could let x be 100. And you wouldn't like graphing this. Okay? So the point being, as far as using the decimal, I can't remember a time when with decimals I would try graphing a line like this. Now there are times, I agree, that in algebra you're going to get equations like this. But when we graph them, we try to write the slope as a ratio of integers so that you can go a run and a rise. Okay, the sun rises over where I run, rise over run. Okay? Let's go back to the document camp. Now that's what made 45 tough. Now I'm going to come down to problems I talked about, and you're going to look at these and you go, oh my goodness. Y equals negative 5. Let's leave that one up there for a bit more. Okay, y equals negative 5. Okay, so I'm over here on the side. I'm going to run again, just a small coordinate system. Okay, and the problem was y equals negative 5. Now if I think of a t-table, and I'm going to mess up, if you like afternoon tea, like the English, and I keep talking about t-tables, and you have in mind something pleasant, and we're doing graphing, this may mess with your head a little bit, but I'm saying y is always negative 5, so it doesn't matter if x is 2, or x is 0, or x is 10, y is always what? Negative 5. No matter what x is, y is negative 5. So all we do is come down to, there's 1, 2, 3, 4, 5. So it's going to be a horizontal line through that particular intercept, and there is y equals negative 5. Y is always the same value. That's it.
So what I was trying to figure out.
Because y is always negative 5 for no matter what x is. This is like saying I have this equation. 0 times x plus y equals negative 5. That's the same. Okay, let me get rid of that. 5 didn't look very elegant. So I'm going to go ahead and make that a nicer looking 5. But 0 times x plus y equals negative 5. It's the same as the equation y equals negative 5. Now, no matter what x you put in here, 0 times x is 0. 0 times x is always 0 no matter what x is. So put it whatever x's you want, y is negative 5. Okay, let's go back to the document, Cam. Now I'm just going to go next door and slide over. Okay, let's look at this one. X is negative 6. Okay, so up here I'm going to put now x is negative 6, but I could write that as x plus 0 times y equals what? Negative 6. Do we agree? So if I do that, no matter what I put for y, I get what? Negative 6. So another t-table. And after a while, you don't need to do tables with these. I think you'll just understand that no matter what y is, make that minus 3, make it a 5, make it a 10, doesn't matter. What is x? Negative 6, negative 6, negative 6. So that says come over now to what? 1, 2, 3, 4, 5, 6. So here's negative 6 right over here. And I'm going to have what? A vertical line. Done. And this is the line x equals negative 6. So if you have x equals something, it's a vertical line. If you have y equals something, it's a horizontal line. End of story. Now, I try to explain it through this table with the idea of taking this up here. And let me get that again. It's not reading very well because of the distance. So I will rewrite it as x plus 0 times y is equal to negative 6. And no matter what y is, x is negative 6. That's what this table says. Again, there's certain things you have to memorize. You have to memorize that if x is a constant, that's what we mean by x equals negative 6, that x is a constant. And I keep looking at what I'm seeing on the monitor, and I don't like what I'm seeing. I'm not making my numbers and letters large enough to be seen. But when I say x equals something, then I just go over in the x-axis that far and draw a vertical line. If y is equal to something, I go on the vertical axis to that value and then draw a horizontal line. There's certain things you need to perhaps store in your memory. Now what we've done is talk about slope-intercept, standard form, two intercepts, and the idea of horizontal and vertical lines. I've talked about slope, And again, one night, I realize, is not enough to completely master this. But I ask you to spend 3 hours on it so you would get some frustration going, get some involvement going, and gain on it. And if you did that, that's what I expected. Sarah and I had quite a discussion of this over dinner last night with the idea of I had pushed much further, and I explained my justification for it. We were interested to see how successful you were today. So I'll report at dinner tonight how things went. And the question is, can you have more time to get these problems done? Well, if you need more time to get them done, as long as you put your time in last night, then yes, I want them done, and I want you to feel comfortable with them. Okay? But the idea is learn how to graph lines and learn the vocabulary of it.
Vocabulary is really important.
Yes, the vocabulary is terribly important. So let me come back to the document cam for a moment. Okay, now if I look, coming off there, at these two problems, my suspicion is these two problems suddenly look like a piece of cake. Let me bring that in tighter. X equals what? 7. So what is it going to be? Describe for me. No, I want to know what will the graph look like. Describe it for me. It's going to be a line. Good. What kind of line? Vertical, horizontal, or diagonal? It's a vertical because X is always 7. A vertical line through 7. Okay, coming off there, we go to number 50. Describe the line. Horizontal line going through, on the vertical axis, going through a 4. So you could do 1,000 of these as long as you remember that. If you forget it, then you're in trouble. Okay? So let's look at something like 44. What do you think your choices would be if you were just to do this with points? Let's go to 44. What would you try doing on 44? Okay, converting something, I hear, to a decimal, not in your life. Okay, I'm hearing something about the 3 and cross-canceling. Okay, let's try 1/3 x plus y is equal to -1. Now, I heard a suggestion, let's multiply both sides by 3. Okay, x plus 3y is equal to -3. I can go with that. Do you gain anything? Well, it depends whether you like the 1/3 or not. But remember, I'm hunting for a table of values for a moment. So I'm thinking of a table of values. Okay? So a table of values. My x's, my y's. And as I do that, I'm going back to Jessica's observation. If I leave it in this form, I want x as a multiple of 3. So what is a multiple of 3 I could use? How about 3? Or a 6, or a 9, or a 12, or a, how about a -3? Okay, so -3 would work also. Well, if x is 3, what's y? Okay, I've heard several. Okay, if x is 3, 1/3 x is going to be 1. So if x is 1, what must y equal to equal -1? I'm hearing -1, I'm hearing 0, none of the above. 1 plus y must be -1. What do I have to add to 1 to get -1? A negative what? 2. Oh. If you have 1 plus y equals -1, subtract 1 from both sides, y equals -2. Arg. Okay, I'm afraid to ask what happens when x is negative 3. Okay, if x is negative 3, I have 1/3 times negative 3 plus y must equal negative 1. What does this become? No. Negative 1. The 3's do cancel. I agree, but that gives you a negative 1 when you cancel. So what must y equal if you're going to add y to negative 1 and get negative 1? If I start with negative 1 and I add something to it and I want an answer in negative 1, doesn't it have to be a 0? Additive identity? No, not additive inverse, the additive identity. 0 added to negative 1 gives you negative 1. If you don't see that, then try adding 1 to both sides. What do you get? Y equals 0. Okay. I realize you don't like it because you're not having success. But these last few questions are what we spent a whole lot of our time at the beginning of the semester trying to do those things, and they are what that kind of difficulty. What can I add to negative 1 and get negative 1? And if you cannot see that as a 0 at the moment, that means you aren't seeing something clearly that you should have seen 12 weeks ago, and it's going to be the devil for you in a 70, because that's going to be expected, that you can sit there and say minus 1 plus y equals negative 1, y equals 0, and go past it in 10 seconds and say, oh yeah. Okay, you said that we could try 6. I'm going to do a few more of these because we're clearly having trouble. If x is 6, what is 1/3 6? One-third times 6. Very good. It is 2. I like that. But I want to know what y is. So this cancels, giving me a 2. What do I have to... We're doing Austrian subtraction. What do I have to add to 2 to get negative 1? Negative 3. This became 2 plus y equals negative 1. Now, what I want you to realize is that at this point in the semester, we are at the end, as Jim Morrison would say. The end. If I give you that equation, you should, you must, you have to, non-negotiable. You have to be able to understand that I can subtract 2 from both sides and solve for y and get that solution. That is mandatory. If you are finishing a Math 20 and you're passing, you have to be able to do that calculation. This isn't negotiable. And if you go into a 70 and you can't do that calculation, you probably aren't going to survive. It's that straightforward. So this tells me that when x was 6, y was negative 3. That is another ordered pair. And I can do this forever. Now, it is clear this is not a technique that you're going to do well in right now. So let me start with the equation again. My equation was 1/3 x plus y equaled negative 1. So I don't want to leave it in that form. I'm going to write it in slope-intercept. Get y by itself. What will it read? Y by itself. How do I get rid of a term? I subtract it, right? I want to get that term out of the left side. So I'm going to subtract 1/3 x from both sides. What does that give me on the right side? Negative 1/3 x minus 1. Do you follow that step? Okay. What does the negative 1 represent?
Y.
And what is b? What does it represent? What does this part represent? No, it's not the slope. It's the what? B, as in bad. Y-intercept. Good. So I draw a coordinate system. Put an x, put a y. Scale it. Okay, there's negative 1. Bingo, I have 1 and 2 points. And all I need is 2 to graph the line. The constant, when I solve for y by itself, is the intercept. It is 0 minus 1. That is the point I just graphed. 0 minus 1. Now, how do I get other points? And I shouldn't have put that close to there, so let me run that over here at 0, negative 1, because I have a slope of what in this form? My slope is negative 1/3. So note, slope is negative 1 over 3. And what does the 3 represent? Rise or run? Always over the run. Okay, so that says take a run. Start it. This is the starting line, your intercept, and we're going for a run. Okay, so we're going to run 3 paces. 1, 2, 3. Okay, I stop there. That's as far as I get to run. And then I'm supposed to rise what? Negative 1, which means I go down 1, and that is my new point. So there is my rise and run. This was 1, 2, 3, and this is a negative 1. I went over 3, down 1. Join the points, and I have my line. Again, at this point, and I don't mean that in terms of a pun, that was poorly selected. With what we've done, there are a couple things that you're going to have to, I think, accept. First, it's going to seem a little bit strange to you to do the things that I'm asking you to do. They are strange and uncomfortable because you haven't done them before. Now, there's a difference in that and getting lost. If I give you the directions, then you just have to follow the directions. You just don't feel comfortable in where you're going. To some extent, this is like a Field of Dreams, that movie. Now, you build the baseball field, and they will come. Do this process enough times, and I think your comfort zone is going to get better. But the language is important, and to recognize what information you're getting when you have it in this form. The slope is the coefficient of x. This constant is where you cut the vertical axis. What do you do with the slope once you have it? Once you get the intercept, take the denominator of the slope, and it's always going to be positive. I never run the denominator as a negative. If I have a negative slope, the numerator is always going to be the negative. So I always start at the intercept and go with the run. It'll always be to the right. Now, if the numerator is positive, you go up. If it's negative, you go down. You have a second point. Join the 2 points. You have your line. Michael. I have a choice on a fraction that's negative of where I want to put the negative sign. So if I have a slope that's negative, I always run the numerator the negative number and the denominator the positive number. So the run will always be positive. I will always go to the right and then either go up or go down depending on whether the numerator, the rise, was negative or positive. Okay, now, we always talk about going from left to right. Remember I said yesterday or the day before where we had P1 and P2? P1 is on the left, P2 in the right. I'm going from left to right. If I'm going downhill, the slope is negative. Sure enough, negative 1/3. I'm going downhill. If you're riding a bike, it's a nice place to be going. If you're going uphill on your ride, then your slope's positive. So if I looked at this equation, just a minute. Okay. So I have the same intercept, right? Negative 1. The only difference is I've gone from what? A negative 1/3 to a positive 1/3. So when I went over my 3, instead of going down, I went up. And so this would be that line. And notice that this line is going uphill. Positive slope. And if I gave you, now I'm going to give you the 2 equations at the same time. If I gave you these 2 equations at the same time, then the point where they meet is called the simultaneous solution. So the solution to this system of equations is the ordered pair 0, -1. And we solve that using a graph. And that's, strictly speaking, a beginning algebra problem. We call that a simultaneous solution of a system of linear equations. We call them linear equations very simply. You get a line when you graph the points that are on them. And what I also want you to realize, and Ernie, let's slide over now. We're going to pan to the left, coming back to here. We were hunting for points, right? We found 3 of them. And I said you could find 4, and then 5, and then 6. You could never stop, and you'd keep finding points. These are all the points that are going to be on this line. Okay? Or in this form, same equation. The same line, different form of the equation. These are the solutions, these pairs of numbers that will satisfy that equation. There is no one solution, an infinite number of points. Now if I pan back, Ernie, to where I was, we need a, something that says, press the button, it goes back to where you were, sort of like a redial. This is a common point that makes both equations true, and there's only a single point that'll do that. So this is a unique single point that makes both equations true at the same time. Hence, simultaneous solution. Michael.
So all the equations and stuff we've been solving all semester, we've been building this up to do this.
Okay, the question is, we've been going along, doing a lot of neat things for a whole semester. I padded your statement a bit. But we've been going along all this time. Is this what we've been leading to? Yeah, this and more. Because I'm going to look now at a slightly different equation, which is what the next section is about. But I'm going to ask, what would happen as we now pan further to the right, Ernie? Now, we have these two to contrast. Now, a lot of what we're doing is trying to get to graphing general expressions. So to a degree, this whole point in graphing and such in application has to do with curves. Generically speaking, a line is considered a curve. Okay, now, this we called a linear equation in two unknowns. And if I rewrite this, this becomes y equals negative 1 over 1x plus 1. Negative x has a coefficient of negative 1. So the slope is negative 1 over 1. So that says go over 1, down 1, and you're at your point. And the intercept is at 1. So we know how to graph that pretty fast. And this is, by the way, why many of us in our department will not allow a graphing calculator, because you need to know this stuff in your head. So the intercept is 1, and this says go over 1, down 1, there's my another point, and here's my graph. And I expect you in an algebra class to do it that fast. Now that is considered a linear equation. Its graph is a line. What about this? This is a second degree equation in two variables. Now that's going to turn out to be a circle. If you look at the points on here, let's try this now. If x is 0, what values of y will work? If x is 0, y squared must be 1. So what must y equal? What? Okay. 1. Okay, I'll go with that. What else? Wouldn't it also be true if y were negative 1? And if y is 0, what must x equal? 1 or negative 1. Not doing my circles so great as I try to do it in this way. But the idea is that you just get a circle of points that satisfy that particular equation. So for example, if I had x is 1 over the square root of 2 and square it, I get 1/2. And if y is 1 over the square root of 2 and I square it, I get 1/2, and 1/2 plus 1/2 is 1. So if I take 1 over the square root of 2 for x and 1 over the square root of 2 to y, I'm going to have the number I need, which is about 0.7. So if I go over 0.7, I go up 0.7, and bingo, I'm on the line, or on the curve. Infinitely many points in the circle. Okay, I'm going to leave that for a moment, Ernie, and I'm going to come over here to what we've been doing. There's a section I did not cover, per se, and it's the last section, which is applications involving graphing, and I'm not going to go there, but I want to come back to, I think, let's go back to that sideboard, a couple of closing comments here, back to where we were. We did a problem earlier, y equals, let's see what it was. Y equals negative 3/4 x, correct? And we said that was a line going through the origin. I could just do y equals x. So when I think of that problem, and I think of now, and Ernie, you're going to have to give me some space. I went off camera there while you were not looking. Okay, I'm going to come over here. Now, as I do this, x is 0, y is 0, and the slope is understood to be 1 over 1. So that says go over 1, up 1, and I get a line going through the origin. It's a diagonal of a square. What happens if I take y equals x squared? Well, that again is a second degree equation, and that's the kind of thing we do. And it starts at 0, it's 1, 1, but it does this. And that's called the parabolic arc, which is the suspension bridge cables on the Golden Gate Bridge that you observe. They just come down like this, and now you have the Golden Gate Bridge. Now, these second degree equations are where you're headed. And these all, now the equations are the circle. This was the parabola. Looks like parabola. Parabola. We talked about the circle. You've all seen an oval. That's called an ellipse. And then there is another set of curves called hyperbolas. But these all come from ice cream cones. So if you sit there and look at an ice cream cone, the sugar cone, the top's a circle. If you chew it in a very special way, then you get the oval. And if you chew it in another way, you get the parabola. And then if you take two cones and cut them, you get the hyperbola. They are called cone sections from ice cream cones. Conic sections. That's where you'll be headed in the courses to come. Okay, I'm going to close this part.